So George left out that we're also colleagues and classmates when we were graduate students at Berkeley, just a year or so apart. So it's a great pleasure to be here in San Diego. I come here from New York, where you know Hurricane Sandy came through. Actually, upstate New York, so it was not as bad as what you see on TV. But as we speak right now, it is actually snowing. So it's nice to be here instead of in the snow. So this is work with SoNIC, Software Network Interface Card, and it's work with my students, Kisa Lee and Han Wang. So I actually have a quad chart here that is required that you do for some of the DARPA grants that you get. And I thought that it's useful for anybody out there, if you want to see some of the work that I work on, the research that I do, this lists quite a bit of that in a compact form. So one of the things that bring me here today, and one of the grants that I have from NSF, is the Future Internet Architecture. What does that look like? And the specific grant that I'm on says the future internet architecture looks like one where there's this global set of data centers connected via the network in the middle, in the core of the network. And then you have a network that connects this core, these data centers, to the edges. And so this hidden internet, Google, Facebook, Amazon, Yahoo, all have a set of data centers that they manage, so it's within a single administrative domain, and then they have often fiber networks that connect these data centers. And so some of the characteristics of this network, future network if you will, is that you have fiber or lambda networks. It's private or semi-private where you don't have a lot of cross-traffic on each link. And it's pretty much owned by a single entity. So Google has their own fiber. Yahoo has their own fiber, like I said. You also have some other players getting into this. So you have the national lambda rails. So we have universities and government. We also have the military interested in the cloud and this future internet as well. And so some of the issues that some of the things that you would think about this is that performance on this network would be great, especially since there's no cross-traffic. However, there still remains to be quite a bit of challenges. There's a paper trail here that actually lists some issues with performance on these lambda networks, this future internet architecture. Namely being that even though you're sending over something that pretty much you own and only you use, it was still possible to observe packet loss. And if you observe packet loss in a high bandwidth, high delay network, that actually destroys your TCP throughput performance. And so some of the papers here, namely the FAST paper in 2009 actually characterized a system called smoke and mirrors, where we actually used this wide area network as an extra storage medium. So once it was in the fiber, we said that it was safe. And what we found out in that paper was once the packets didn't always make it to the other end as we expected. This then led into another series of papers. DSN and the IMC paper looked at how that loss could actually occur. The NSDI paper, which actually came first, assumed that you would have loss in the network and it used forward error correction to mask that loss. The DSN and IMC actually found out that the loss was actually occurring at the end host. And so the question was, how could loss occur at the end host if the link itself, the path itself, was pretty much uncongested? Some of the other issues that still exist are jitter can get introduced even though you have this isolated network. And you can still see packet trains. Often that was assumed to be caused if you actually had cross-traffic. So if you have little to no cross-traffic, how are you actually seeing quite a bit of jitter and packet trains? When you talk to the military and whatnot, there's concern with rogue routers that can actually infiltrate your network and exfiltrate data. So actually listen on the network and at some point start sending packets to some machine that's not within your secure network. So how can you detect and prevent that within your network? And then finally, again with security, if you think of a WikiLeaks example, is there some way that from an end-to-end point of view, you could actually send data from one host to another in a way that's completely undetectable? And so these were some questions that we were looking at within this, this new network, this future internet architecture, where you have this cloud, this global set of data centers in the middle. And we wanted to see if we could actually make some progress in answering these questions. And a key that we needed, that we didn't have before, at least we being systems researchers, systems and some level of network researchers, was we didn't have view in the network. View, and when I say view into the network, I mean view into the entire network stack and all the elements within the network itself. You know, there are routers and switches, there are line cards, there are a number of elements that actually impact security and performance from an end-to-end point of view. How are those impacting the security and performance? So we needed some way to have a view of this. And our approach was, again, as systems people, we often, I would say, are kind of afraid of hardware and afraid of layer 1 and 2. Now, my undergrad is actually computer engineering. So I did a lot of embedded systems and circuit design, but my PhD was all distributed systems. And so since going in a PhD, I had not looked below layer 3 at all and hadn't touched any hardware for the most part. And so I'll actually get into how layer 1 and 2 impacted performance a little bit later, but the key was that there was no easy way to figure out what was going on. And so our solution to this was to have somehow provide some easy access to the entire network stack. And that's where SoNIC comes from. We want to understand the network using some software-defined network interface approach. You can think of this very much like software-defined radio. So in that sense, it's orthogonal to software-defined networking, which really is at layer 3, and is really closer to software-defined radio, which is really more layer 1 and 2 of a wireless network. So what we want to do is to use this software approach so that we can actually understand the network better, and then we can use that to improve the performance, the availability, and security of our network. So we're going to actually build some platform that gives us access to everything in blue, this entire network stack, and it's going to be all entirely software access. And it's going to be not at scale, but at line rate. So it's going to be at line rate and in real time. And the real distinguishing characteristics here is that the software, like I said, is going to be real time, but it's going to determine what's actually sent. So for example, you could change the line encoding in a wired network just like you could change the MAC protocol in a software radio network, except you can do this in software. So we're not going to touch the hardware at all to do this. And so SoNIC is both the hardware and part of the software, and this hardware board that we have is going to actually do the physical sending and receiving.
So I'm just trying to understand the motivation a little bit. So in the wireless space, you know, white spaces or whatever you want to call the buzzword, I mean, there's a pretty clear motivation for, you know, you're dealing with a crowded space. The spectrum is occupied by incumbents. You're trying to dance them around. So forth. The picture that you showed us, this is your private network, your own lambdas. Why would I, on the fly, want to be messing with low-level info? I mean, isn't there an optimal point that I set and forget?
Yeah. So there's you said set and forget. You said was that the last thing?
I mean, for any given cabling and distance and dispersion and so forth.
Yeah.
You know, I could imagine that I want to tune that.
Yeah. So
why do I need sort of software real-time access to that?
Yeah, so that's a very good question. So it turns out that layer 1 and 2 can actually impact your performance within and between the data center. And it's not just physical cabling, but could actually be dependent on the workload as well. But you would never know. So that's the key, is that you want some easy access. The real-time allows you to really is a response to the way we did it before. There's actually, the previous paper is from IMC, and the way that we did something very similar was offline, where in the sense that we actually use physics equipment to do some of the stuff to do everything that I show you here. And then later on, 2 days later, we then had what the distribution of inter-packet arrival time and all this other stuff was. So this can actually give you the traffic characteristics in real time. It also could potentially allow you to respond to that. And a good example of that is that inter-packet spacing actually does impact performance for TCP flows. If you have a lot of batching, that actually does reduce good put a bit, even if you don't have loss. And so you could actually use something like this to make that inter-packet spacing, well, first of all, know what it was, that distribution, and second of all, somehow change it. So this gives you that level of control, that level of view at that low level. So. Yeah. So yeah. So no, that's a question. I said that, and you can. Whether you would actually do that in a data center is another question. But however, in real time. However, you could use the same platform for 1G and 10G, and they have different line encodings for that. But you wouldn't just dynamically change the line encoding unless the other end had that as well. And why would you even do that to begin with, unless you're playing with new protocols? But that doesn't necessarily need to be real time. So, in any case, this is you actually get at another heart of this, which is this is a research platform. It's one that you could use to easily ask questions. And it could be perhaps that changing the line encoding could get you better performance. It's a question that a systems person probably would not normally ask. And this one you could actually fairly easily ask, if I change the line encoding within a data center, would that change things? Anyways, you could do that. I won't talk any further about that. Now, this is to say that this will primarily allow you software access to layer 1 and 2. Layer 3 is still software-defined networking, where they separate out the data plane from the control plane. And there I do have a separate paper, which was in ANCS earlier this week, NetSlice, which is like route bricks, if you know what that is. So I won't talk about that. I'll talk mostly about software access to layer 1 and 2, as opposed to software access to layer 3. Okay, so let's go into SoNIC and some of the comparisons, and I'll talk about some of the applications. So the key here is that in a normal setup, you have a network interface card or even a router or whatnot, and that handles most of the layer 1 and 2 and the interaction with that. And so as a systems person, someone who's at the software side, you normally wouldn't touch layer 1 at all. And as I said, it can actually impact performance. This just shows that part of that is that 10 gigabit Ethernet is continuous, so you're always sending at 10 gigabit. And it's this reconciliation sublayer that if you're not sending data, it'll send idle symbols. SoNIC, then again, is going to push that boundary down so that the NIC, the network interface card, just does the physical receiving and sending of on the medium and the analog to digital, the serialization and the deserialization. That's what the hardware is going to do. And then anything else is going to be done in software. So the physical medium detachment, the interacting with the wire, and the physical medium dependent, and the physical medium attachment, the serialization and deserialization, that's going to be done in hardware. But the physical coding sublayer, the actual encoding, the actual scrambling of the bits, the MAC layer is going to be done in software. Another question that people often ask is, how does this compare to NetFPGA? NetFPGA is, they have a similar board. In fact, these boards are from the same company, High Tech Global. But the motivation is different. In NetFPGA, you are looking at some hardware platform for routers, but also oftentimes people are not only pushing layer 2 down in the hardware, but also layer 3. Whereas the difference here is we are pushing layer 1 and up into software. So in that sense, they are orthogonal. And in fact, you could use a little bit.
So just a question. So on the 10G FPGA, there's a net logic chip that sits between the cage and the vertex. Is there, I'm trying to understand where this is. Is there actually a PHY chip that sits behind your SFP cage, or is that straight wired into that FPGA? Because there has to be some sort of clock data recovery. So where, is there a PHY chip there?
Yeah, so that's an excellent question. So there is a net logic chip that provides the clock, but there's not a PHY chip that does all of the PHY encoding and decoding and stuff like that that's done here, which is actually the whole reason that we went with a different board, was we couldn't get access to this physical coding sublayer with the NetFPGA board because of that PHY chip. And so we went with a different board which would allow us to get access to that. The NetFPGA did too much for what we wanted. Does that make sense?
Yeah. So,
and there is a net logic chip, and we use that to provide the clock.
6466 coding is being actually done back in the FPGA?
No. The 6466 bit encoding is being done in software.
Okay. And the software or FPGA is not being done on the PHY chip, correct?
That's right. When I say software, I mean within the host. When I say hardware, I mean within on this board. And let me actually get to that right now. So we have some SFP Plus is the small form factor pluggable, where essentially you plug the wire, the fiber into, or the direct attached cable. And so that's what interacts directly with the medium or the cable. The FPGA, for the most part, does serialization and deserialization. And then once we have the bits, we DMA everything to the host memory. So in that sense, and it's color-coded, so you can see that the physical medium dependent is done by the SFP Plus transceivers there, and then the serialization or the physical medium attachment is done by the FPGA. And then we do a DMA over the PCI bus, and we do the physical coding sublayer in software.
So it's a Gen 2 PCI, you've got 40 gigabits. How does that work?
It works great. No, so that's an excellent question. So it's Gen 2, and the key here is we had to do a couple things. We have two 10 gigabit ports. So one of them is that since we have 64/66 bits, 66 does not fit well in base 2. So we actually do some packing of multiple 64/66 bit blocks in one transaction and whatnot. And we also do virtual PCI bus, so we do some PCI arbitration so that we can have multiple channels over the same bus. And so we did have to do, those are the two big things that we had to do to get that to work.
Sorry to keep asking this. So, in the other board, in the other chip, it actually allows you to do what's called slicing, so that it actually can do quantization, and that actually helps you with equalization and so on. For this one, are you limited to a limiting amplifier where the only thing you're getting out of that PHY layer is either 1 or 0? There's no slicer on this, is there?
Yeah, we're just getting ones and zeros.
Okay.
So, yeah. Just going back historically a little bit, the way we had things set up before, this is the Internet Measurement Conference paper from 2010, was we actually had a laser that we modulated at 13 10.3125 gigabaud, and a router accepted these legal form packets, routed around the network, and then we captured at the other end an oscilloscope. So there we captured the waveform, and we had to then do the synchronization and find the clock and all this other stuff, and then go up the entire stack. We did all of that in software, and that's what, for the most part, made it non-real time. And so what we did is we offloaded essentially the analog to digital to the hardware. And then once we get those ones and zeros, that's then everything that we do in software. And so so we played quite a bit on where to put that boundary to get this to work.
But it also means that the number of Ethernet physical protocols that this card supports is limited. It can't support all of, for example, it can't support LR4 or ER4.
Yeah.
Okay.
So yes.
Okay.
What are those SMAs?
SMA. The 16, the 4x4 grid.
18,
or 18.
SMAs you got sitting there.
Oh, this is a general development board, so we don't use 90% of what's on here. But it had what we needed, which was not to have that PHY chip that George had mentioned. Now in software, so once we then DMA the raw bits to memory, we then do, and again, this is color-coded, so we then do the physical coding sublayer. And so what that does is that takes the Ethernet frame, and that encodes that Ethernet frame into 64-bit blocks. And then to ensure a mix of ones and zeros, the standard then takes those blocks and then scrambles the bits. And so we do the encoding and the scrambling in one core. So each one of these little blocks is a core. And we do that so we're able to maintain line rate at 10 gigabit. And we do the decoding and descrambling on a separate core. Okay? And that's the physical coding sublayer. And then for the layer 2, essentially the CRC, or cyclical redundancy check, we create that with a separate core, and then we verify that with a separate core again. So this has a 4-core solution, and then we have an application core that allows us to interact with the protocol stack at different levels.
So where's the data being generated? Because George Porter could tell you that if it's coming off a disk, you can't spin up enough data to get into your core to then scramble. Are you using PBRSs as dummy data for this? Or where's actually the data that's being scrambled?
Yeah, so the easy way to do it is we have it in memory, and then you have a second or a couple seconds worth of data.
So you burst a couple seconds and then you have to reload.
Yes, essentially. That's the easy way of doing it. But we do actually have some block interface to interact with that. But as you say, that's very slow, and you have to, every cycle counts. So I think you had a paper. Every microsecond counts. Every cycle counts, and you have to be very careful. Some of the optimizations that we had to do was, in order to do the encoding, the scrambling is dependent on the previous state. And so in order to, instead of doing 64 operations essentially, order 64 because you had to touch every bit, we're able to actually get that down to just a couple shifts and a couple XORs. And it's equivalent. So there's quite a bit of, and we also use a new instruction from Intel to do some folding. And so there is quite a bit of optimizations that we had to do to get this to work. And then we also borrow from Sora, which is software radio that was done here by Jeff Volker, so that we essentially remove the scheduler, so these things continuously run on a single core. And then we also have some very efficient FIFO queues to communicate between the cores. And so all of this is able to run and is able to run at that line rate. So we're able to do all of this with multiple ports and actually have it interact with a 10 gigabit link. And it's like I said, so it's software. So you're actually writing something, C code, essentially. This right here is a packet capture and packet generator examples where you define how many packets you may want, the source and destination MAC and IP address, the amount of idle space. So this is between every packet, there's an inter-packet gap. And so this gives you essentially in bytes, but it's actually 7 or 8 bits, the number of characters between each packet. So this will generate, for the generator, this will generate exactly 96 bits or 12 characters between every packet, exactly. And I'll show you that a nice thing that even though it's software is actually very precise. So one of the key reasons, one of the key applications that you would use SoNIC for is actually network measurements. So it's actually very precise. And so this then opens up two different channels, essentially, one for the generator and one for the capturer. And then it starts, it doesn't show it here, but it essentially then starts generating packets. A little bit before that, we have to configure the cores so that they're in the optimal configuration. We generate the packets, and then at the other end, which if you have some loop, there's network element or whatnot, you then capture the packets.
So for network measurement, do I need a main board with 2 separate PCI buses to actually get this to disk, or are you able to spool full 10 gig packet capture?
We're able to spool for full 10 gigabit, but like George was saying, you do have to be careful. If you keep it within a couple seconds, you can essentially use 100 gigabytes of memory or whatnot. If you want to actually continually interact with 100 gigabytes of DRAM, so if you're using DRAM, then you can store 100 gigabytes worth of whatever. What's that? I didn't hear what you said. 100 gigabytes is reasonable. So I'll talk about this a little bit. I just bought a cluster full of machines, and they all have 128 gigabytes.
The short answer is you just take small snippets.
That's the easy way to do it, but there is a way to actually continuously write to disk, but you just have to be careful with that. We have a block device interface. So this doesn't show writing to that, but we give that. Yeah, good question. So the question was, how do we get that precision and get rid of some of the non-determinism? And the key is that we're able to touch every bit. When you're sending at 10 gigabit per second, each bit is about 97, about 100 picoseconds essentially. So when you're able to affect or count every bit, then you have, order 100 picosecond, tenth of a nanosecond precision. And so that's what I'll show you in a second, but we're actually able to generate packets with that precision and measure.
You need that precision since you're using your DMA kind of as a buffer. You just need to get this encoding to keep up, and you'll have a little bit of slop in your DMA because you'll be DMAing in from the NIC to look at it. As long as you maintain.
Yeah. So once you
can take up that slight non-determinism as long as it's not too much, because you're writing the memory and then reading out of it, correct?
Yeah, so we're able to maintain that line rate, and there is a buffer between the hardware and the software, so it takes a little while to actually go through the system. But when you actually, for example, are looking at the timing between packets, you actually have precise timing and control between packets. And so actually, let me. I'll show you that with this, with those top 2 applications, what we can do. So going back to that first example where we're losing packets at the end host, this was motivated because we actually had the National Lambda Rail, which was kind of like this new internet that I was talking about, and the packets were being lost at the end host. And so the question was, how in the world why in the world was the end host dropping packets, especially if you were not sending at that maximum rate. And so what we did with that physics setup and what we're able to do with SoNIC was we're able to then set up an experiment where we generate packets that have uniform spacing between packets. That inner packet gap is the same. It's always, for example, 12 characters or whatever the rate is. It's always the same. And then we're able to generate that traffic. And then we're able to capture at the other end the pattern of the inner packet gap that we receive. And as it turns out, that even though you're in a more or less idle network, that there was no cross traffic, it turned out that there was still batching of traffic. And even though we're sending at 100 megabits per second, we would receive short bursts at 10 gigabits per second. And that's what was shown in that IMC paper, and that's what we're able to re-verify that is the case in general now with SoNIC. Just going through some number of routing elements, and there's some randomness within them, it turns out that the variance actually increases, and you do actually see some batching effect. Now the key here is that without SoNIC or without something that gives you access to layer 1 and 2, these two patterns look the same. The network interface card throws away these idle symbols. You would never know that these patterns were different. Number one, you couldn't generate that, and number two, you couldn't read that out.
You said you're using multiple virtual channels, right?
Within one system. That way we have 2 ports, yes.
Right, so then in that case, they're using different buffers and things like that. So how do you guarantee the passage through the crossbar basically for all the multi-flits?
So the question really is, how do you, is there enough PCI bandwidth for both channels? And the system the motherboard that we have, there's over 100 to 200 gigabytes per second of traffic, so there's enough bandwidth actually for the 2 channels. So that's actually not, we did have to be careful, that's not much of an issue. But another question is, how can you so carefully measure the time between that? And really the answer is we just count the bits between packets. If this is 96 bits, then that, or 100 bits, right? Each bit is 1/10 of a picosecond, so then that's 100 nanoseconds, which is really kind of that minimum spacing.
So
I might be off by order of magnitude.
my 10 gig knowledge is probably old and rusty and outdated, but at least my recollection of the standard, there are actually 4 lanes that are running in parallel, and so the inner packet gap actually has to be has to send you back to
That's
line 1. Or do they?
no. So they're not 4 lanes. No, there's not.
Something like that.
You're talking about on the board,
Yeah.
on the wire. On the board, there's 4 lanes running at 2.15 gigabits per second. Over the wire, it's running at 10.3.
Right, but I thought it had to be synced so that you could always pull it off.
That may be a specific, yeah.
So the connection between the SFP plus module and the FPGA is running at 10.3. It's not using the board. Older technology.
Yeah. So we're not using that. I did skip some steps where we do actually convert the bit width between different.
But could this have been coming, so the interframe gap isn't standard at 96, right?
The minimum interframe gap is 96.
But it goes up, you can go up above that.
Sure.
And that's part of the 10G standard. Could this have just been coming from different vendors doing, because all of this is getting inserted at the line card at some intermediate router
Yeah.
in national bandwidth.
Yeah.
And that might not, because nobody was looking at it, people might not have known even how to set the routers.
Yeah. No. That's an excellent question. Is it just, is it Cisco's fault with that particular CSR1 routers? But it turns out that each router or class of routers does have its own unique qualities on that, the jitter that it imposes. But also, it is the case that as you actually go through more routing elements, then you do occasionally see batching. So it's not a mistake by Cisco.
Because I've seen that they actually try to increase the interframe gap
Yes.
deliberately to prevent
Exactly.
the issue
Yep.
that you're seeing.
That's right. So if you do that, then that would help prevent this. But I don't know how well they're doing that.
Okay.
In fact, that's something you could do with SoNIC, is to measure that and actually enforce it. So the key here is that you need software access to the physical layer in order to understand that performance issue where you're losing packets, and potentially to do something about it, to verify that your router is doing what it's supposed to be doing, which is increasing that spacing.
But this is to play devil's advocate. Do you really need software access to the physical layer? Because all you really want to know is the gaps between packets.
No, you could, no, that's right. You could do this in hardware, but
You can do that with counters.
that's right. So if you have that capability in hardware, but in our research, it wasn't easy to do that. And in fact, we even went the route of using physics pulse-modulated laser and oscilloscope. So we could not easily get this information. There's probably other ways around it. But the key here is that software access makes it just very, very accessible.
Because you need to access the data before it goes to the 64, the 66, 64 decode.
Yeah, because they strip it.
And normally in a file you don't have that, the way to insert.
Yeah, so the key here is that you couldn't do it other ways. It's more palatable to the taste. So this then is for packet generation and packet capture. So this goes along with that code that I showed you. We essentially have here where we would generate packets using that code, create that checksum, do the encoding, decoding, the encoding, scrambling, and then send that out to SFP+. And then the receiver would then descramble and decode it, verify the checksum, and then we would actually, the app is recorded there, so we would actually record those results. These are highlighted because they're necessary to keep the link up to actually continue to send and receive. So when we capture packets, if we're sending at 1 gigabit per second, and if we are using 1,500 byte packets, which is what this shows, the x-axis is the inter-packet gap, and the y-axis is the frequency or histogram, if you will. And so the key here is that using SoNIC, you're able to generate a signal, generate packets with the inter-packet gap with no deviation, no variance, none. It's always the same.
Why does the sender stop sending when it also stops receiving? Is that the standard? And is that a good choice? Or is that
Why does this send? Say that one more time.
you said you have to receive in order to send?
Yeah, so it turns out you have to send something like 128, not Ethernet frames, but 128 blocks or whatnot, just for the link to show that it's up. And so you just have to continue.
Is that in the IEEE standard, or is that?
Yes, it's not something that we created. So this experiment we have. I don't have a picture here, but we have SoNIC-enabled end host connected to a Cisco 6500 switch. So this was something we had to do to keep that link up between a standard switch, and then we had through another port coming back from that switch to the other port of the SoNIC. And so that's how this setup looks like. And so what we're sending to that switch is something with no variance, but it's 1 gigabit rate, data rate, with 1,500 bytes. And then what we measure out is then some distribution of the inter-packet arrival time.
Is the
Inter-packet gap.
there the minimum 96 bits?
No, the red line is the inter-packet gap of 1 gigabit per second with 1,500 byte packets.
So I guess my question is the minimum length that you measured for the interframe gap, is it less than the minimum standard that the protocol demanded?
No.
Okay, so it was still more than 96.
Yes, it was always more than 96. And in this case, there's, this is 113,340 bits between each packet was what we sent. And then it went down to 111,000 and as high as 115,000 bits between every packet. So it didn't go anywhere near that 96 bits, not for one hop. That was actually multi-hop. And in fact, if you were to, so this is some preliminary results where we're trying to mathematically explain some of the results that we had in the earlier paper, which is when you went through multiple, they were 6500 switches. So when you went to multiple 6500 switches, how you ended up with the plurality of inter-packet gaps at the minimum inter-packet gap, which is exactly what we were seeing before. And it turns out that if there's just a little bit of randomness or a little bit of variance, somehow that variance continues to increase, and you end up, we're still in the process of explaining it, but it's encouraging that it's possible to explain what we're observing, which is a plurality of packets with that inter-packet gap. Sorry, the metrics here are a little bit different. This is inter-packet delay in microseconds, but you can go between packets and time, bits and time pretty easily. Inter-packet delay is just from the first bit to the first bit of the next packet. Inter-packet gap is from the last bit of the one packet to the first bit of the next.
So maybe I missed this. I'm just trying to understand. This all makes sense. Why would I care, right? Unless I would have like some mem switch or something that was trying to play in the inter-packet gap. As long as I don't go below the minimum, every NIC should be able to sync and decode. Why?
The reason that you care is that for two reasons. Number one, this can cause loss at the end host. If you are receiving short bursts at 10 gigabit per second and you have some scheduling delay at that end host, it's possible that you overrun a buffer because you're not able to service it fast enough. And you lose
but the difference between 1.2 and 1.4, that's not going to save me, right? If I have a burst,
this is not. This is not. Well, first of all, there is a minimum inter-packet gap or inter-packet delay. Yes, inter-packet delay also includes the packet size. That's why this is a little bit larger. But if you have, and this also doesn't show how many packets I'm receiving in a row with that inter-packet delay. But if you do receive a short burst, and like I said, there's a bunch of ifs there, and you didn't service that queue fast enough, then it may be possible that you overrun a buffer and you lose a packet. Another one is just like George mentioned, which is some routers attempt to spread out that inter-packet gap, because if you have a smaller inter-packet gap, that does actually reduce performance. Batching does impact performance. So this directly relates to performance, and knowing the distribution of inter-packet gap and potentially being able to do something about it can increase your performance within the data center and between.
So it increases my performance.
Your TCP and performance.
Sorry, so, and this is probably just completely my naivete, but it seems like if I run the packet gap as small as possible, that's going to increase the efficiency of my link, to maximize the efficiency of my link. Right? So as long as my NIC is able to sync up and pull the card, the frames off fast enough, I can't do any better than inter-packet gap in terms of efficiency than minimum.
So I think that this is, I'm not sure if we're talking about the same thing. It's not a matter of efficiency. If you have a very small inter-packet gap, that implies a very high data rate, instantaneous data rate. And you're right, your 10 gig NIC should be able to handle 10 gigabit. But usually there's a finite amount of buffer between the NIC and the host. So if the host is not servicing that memory that NIC is using fast enough, then it's going to overwrite some packets and you might drop some packets. Does that make sense? And it's more likely to happen if the NIC is receiving at the maximum rate, writing to that ring buffer, and for some reason you're not able to pull packets off. Yeah, I'm sorry.
If you can handle 1.7, then you can handle 1. But your argument is I may have actually paced it by
Yeah. This is a distribution of just the inter-packet gap between, inter-packet delay between two packets. I need another graph to show you how many packets I'm receiving with that short, in a row, that packet chain, with that short inter-packet gap. And that would tell you how many packets you're receiving at 10 gigabit per second. And then that would tell you, given then the length of your ring buffer, your likelihood of going around and running out of space. So this doesn't show you that whole picture. It just implies that that can happen. And if you see this, then potentially there are some knobs that you could do something about that.
I find this fascinating because the whole interframe gap is left over from the simplex 10 meg carrier sense where you had to literally wait to listen and then send. So they put this in the 10G standard only to be backwardly compatible with that old standard.
I mean, if you want 10G too, you're going to need it.
I'm not sure that's true though, right?
No, that was the reason.
No, there's an elastic receive buffer on the receiver.
Well, right, but
their clocks aren't super.
But they're full. No, it's full duplex. Why should it matter on a full duplex link?
The sender and receiver's clocks aren't synchronized, so you need that interframe gap in order to adjust the number.
But you can just do that in a buffer. You wouldn't necessarily need a gap between the hosts to do that.
I mean, you're synced up. You're sending constant symbols.
Yeah,
whether the packet symbols or data symbols doesn't matter.
I mean, there's no question there's a synchronization.
What you're saying is that happens at layer 1 and the layer 2 interframe gaps.
But I just find it amusing that this problem is occurring because they made this part of the standard backwardly compatible.
It's not clear that that's exactly the problem because there is a little bit of cross traffic. There is a little bit of randomness in servicing each packet, and that that delay, and that's what we're seeing here.
This allows you to resync it effectively. So
yeah.
By putting that gap in, it makes the syncing.
Yeah, exactly.
It makes the syncing of the 10G a little bit easier.
Yes.
But to Alex's point, if you are truly synced, you shouldn't need this.
Yes.
This is a little bit of slop to make it a little bit easier.
Yeah.
Yeah.
And so, just as an aside, you're supposed to send with 96 bits between each packet, but you're actually supposed to receive with smaller. Our understanding is 40 bits. And so if you actually send at the maximum rate with the smallest packet size, the router is allowed to actually drop packets because you would actually be you'd actually have less than 96 bits between every packet. But so let me move on to then the rogue router. So what we want to do here is can you identify each router? I showed you essentially a distribution of a 6500 router. How do other routers look? So now I'm sending 6 gigabit per second. I could have sent one here with 1500 byte packets. And I have 3 different types of routers and 2 different companies and even a different class within that company. And you could see that there's quite a bit of difference in their inter-packet gap distribution. Okay? And so the question then is, so the key here is that you can then fingerprint, if you will, different class of routers. And you could use this to see if routers are behaving normally. You can use this to maybe see what type of routers are on a network path from source to destination.
How sensitive is those signature related operation environments?
That's a very good question. So this signature could be related to the actual traffic that's being sent. It also is different to the data rate that we send and the data rate that we send. And so the key here is that the distribution does look a little bit different, but all that considered, is there a way to then send some traffic through and be able to just tell what type of routers are in that path, given that there may be some cover traffic and stuff like that. And so again, this shows the red line is what we're sending, the blue is the inter-packet gap of what we receive. Some of you are using a net FPGA. This is actually our characterizing net FPGA. which actually adds quite a bit of jitter when it's used as a switch. And so the last thing that this is just showing that if you were to use Genie, you could use that to maybe figure out, or some network to figure out what type of routers are on the network. And so the last one was, is there a way that I can communicate from one end host to another in a way that's undetectable? And so again, this uses the, we'll end up using the profiling that I showed you in the last set of slides. But the key here is for covert channels, there's normally two types, a storage channel and a timing channel. With the storage channel, we're going to change bits within a packet if it's at layer 3. If it's a timing channel, we're going to change the timing between packets. And so there's quite a bit of work on covert storage and timing channels. But most of it's been done at layer 3 and above, playing with, like I said, TCP headers and the inter-packet gap between packets. As far as we know, there hasn't been much work done using similar techniques, but at layer 1. So what happens if we were to use a 10 gigabit Ethernet standard, that encoding, decoding for a storage channel, or we were able to use the spacing between packets to create a timing channel? And we did this at layer 1. Hold on one second. Hold your thought. And so the key here is that this shows the an encoding table. We have here a starter frame characters, starter frame blocks, excuse me, end of frame blocks. E is an idle block, and then you have a data block. And so if I want to create a storage channel, I would need to find some blocks that are not interpreted. And so this just shows that the way this 10 gigabit Ethernet standard works, I have a starter frame block, a bunch of data blocks that represent my Ethernet frame, and then an end of frame block, and then some number of, each block is 64 bits, and then some number of idle blocks in between. Okay? And so the key here is that I can actually create a storage channel using some bits that are not interpreted at all. So everything highlighted there in yellow are not interpreted by the standard. So we've actually used this to create a storage channel at layer 2 or 1. We can also use the space between packets, so playing with some number of idle blocks to create timing channels. So one question is, does this actually work? If we actually play with those bits that I showed you in yellow, and you may not have noticed it, but they were always at a starter frame or end of frame block. If I use those, does it actually work? And the answer is yes, it does work, but it doesn't actually transfer between through a router. So you actually need to be physically connected to each other in order to have that channel. So that's limited. But for a timing channel, if I'm modulating the bits between packets, can I get that to work? And the answer is yes. So by modulating the space here from 10 to 100 nanoseconds, I can actually create a timing channel where the bit error rate actually is less than 1%. And it goes through multiple hops. So we've tested this up to 3 or 4 hops, and we're able to communicate. People often ask, well, what's the data rate of your covert channel? So if you notice, the data rate of a covert channel is dependent on the packet rate or frame rate of the actual traffic.
So each idle block, you're going to encode 1 bit of your covert channel?
Between each packet, we're going to encode a 0 or 1. Now, actually, I talked to Stefan yesterday. He said, well, if you have so much fidelity, can't you encode multiple bits? And so the answer to that is yes, but we haven't tested that. So we either going to, what we have tested is we either encode a 1 or a 0. And we can get that to work. And then we can also use that using what George mentioned to prevent covert channels by having making sure that the time between packets is fairly uniform. So this is some stuff that we can use SoNIC for. And so with that, I just want to say one other thing about this, that we have a DURUP, a Department of Defense University Research Instrumentation Program, where we bought a number of boards, and we're looking for partners to use those boards so that you can actually do wide area experiments using SoNIC. You could also buy a board directly from High Tech Global and use our software on top of that. We're also working on getting the FPGA to work in a SoNIC form. Okay, so fortunately, that's my last slide. And so, so the key here is that SoNIC does actually work. It works at line rate. It works for very precise network measurements. It's available to use. One of the things that we like to do is create a software-defined network measurement test bed. So we'd be, love to have you if you're interested in using it. Okay. Thank you.